Okay, welcome. So, what we're going to be getting into today is one of the last couple of topics of mechanics that we're going to be talking about, and that is going to be the topic of energy. So, this is generally a fairly big topic, but what I want to start with is this example problem. So, hopefully, you can see that now. I suggest you pause the video, see if you can use what we've learned about kinematics. You should be able to do this with a combination of Newton's second law, so your free body diagram, and the kinematics equations we've talked about. But I'm going to go ahead and solve this. So if you paused and did it on yourself, that's great. But basically, so we're going to have our force of gravity on this box. That'll be 30 times or mg, which would just be 30 times 10, which would be 300 newtons. It's horizontal, so the normal is pointing straight up in this case. And there's nothing angled, so we've got the applied force at 500 newtons. Um, these two are then equal. So normal is also going to be 300 newtons. And then you have your kinetic friction force. So F sub K, and that's going to be 0.1 N, which would just be 30 newtons. Okay. So from there, you can do your sum of the forces. And the only one that's really relevant is the X. So you'd have that 500 from the applied force minus the 30, and you'd get 470 newtons. Okay. And then from there, you can do, okay, F sub X equals MA sub X. That's applying Newton's second law. I should do the sum just so we know it's the net force. So we can then, find the find the acceleration. So we have 470 equals 30 times a sub x. And this is going to end up being 47 over 3, which is a little more than 15. Not this is a bit unrealistic for being able to sustain this kind of thing. You're probably not going to get that kind of acceleration. So we'll just go ahead and do it. And it's 15.7. So a sub x equals 15.7 meters per second squared. Now we want to know how fast it's going after 2 meters. The kinematics equation we'll want to use is v final squared equals 2 a sub x v final x squared delta x plus v initial squared. Now it's not said in here, but I really should have, and you may have figured this out. It's really starting from rest. You'd want it to indicate that, but that's no big deal. Okay, so from there we know that v naught is equal to 0. We have a sub x. We're looking for v final sub x, and we know that delta x is equal to 2. Okay, so we get v final x squared equals 2 times 15.7 times 2 is equal to, then just plus 0. Okay, so we do that and we multiply that by 4, and I get 62. I also didn't round, so I get not 66, but 62 point, and I'll just leave it 667 is equal to v final squared. And then I'm just going to need to take a square root. And when I do that, I get v final squared. I get v final is equal to 7.92 meters per second. Okay, so that is using the combination of Newton's law and kinematics. And really, when we start breaking into energy, this is kind of what we're going to be doing. Okay. Now, before I show you how really the energy equations we're going to be dealing with kind of result from a combination of Newton's second law as well as that equation, that time independent equation, for kinematics. I just want to just briefly talk about what the concept of energy is in physics, and it turns out in other fields as well. Energy is a concept that really does move across a lot of different fields. But basically, the way we can think about this, it is a quantity that is conserved when physical processes occur. Now, I would not call that the definition, but that is a very important attribute of energy. And that is actually why energy is useful. We could calculate whole bunches of quantities about different systems, but the not all of them will be conserved. The ones that are conserved when something happens to a system, those are the ones that are most interesting. So this is why energy is useful. Now, the common definition, I think if you were to look up the definition of energy on Google or something, what you would find is that energy is the capacity to do work. Um, Now we don't really know what work means in this context, so this ends up being a somewhat circular definition. And a lot of times work, when we get to physics, or when we define work in a physics context, we will talk about energy, work as a method to increase the energy of the system. So, like I say, they're a little bit circular. But basically, the way I think it's useful to think about energy, it's this quantity that is conserved among processes. Now, what does that make it useful? Well, it makes it useful because energy is converted. Okay. When you look at any physical process, energy, some sort of energy conversion is going on there. Okay. And if you know that the total amount of energy stays the same and you're just running down, what it was converted to, well, that makes the problem a little bit more tractable. Okay. And it also gives you an idea of, what something can do. So, what the capacity of something. So if you're given, this chemical, this, hydrocarbon chemical, say, and you're told it has this much chemical energy, the idea there is that what that's telling you, that's giving you information about, well, if you did the chemical conversion correctly, what kind of useful motion could you get out of this? Or in some cases, what kind of other energy could you get out of it, depending on what kind of energy you wanted. Um, Work is basically an applied force, and the way you can kind of think about it, it's a force applied over a distance. We'll get into that in a minute, but the way you can kind of think about it is that work is sort of the thing that humans are most often interested in. They're interested in applying forces over distances. That's basically how useful things get done for human beings. You need to apply a force and you need to use that force to move things around. Now, that's a very simplified view of useful work for human beings, but that is kind of the way that you can think about it. Okay. And so defining energy as the capacity to do work, it's really talking about, okay, how much of this useful force, this useful activity of using a force to move an object could you get from a particular form of energy, or a particular engine, something like that. Okay, so that's really what we're talking about when we're talking about energy. So energy is converted from one form to another. All right. Now, in the context of of physics, one of the things we can do is basically what we're going to do. We're going to take F net equals ma, and we're also going to take v final squared equals 2a delta x plus v initial squared, and we're basically going to combine these two. Now, in this context, what we're going to do is we're actually going to eliminate the acceleration. So what I can do is I can solve for acceleration. Acceleration is equals to F net over m. And then what I'm going to do is throw this into here. Okay. And what you do when you do that is you get v final squared equals 2 F net over m delta x plus v initial squared. Now, this gets rearranged. It's useful to rearrange this thing. And generally, what you'll do first is you'll move the v initial over to the other side. So 2 f net delta x over m. And then you'll get the f net delta x term alone. So f net delta x in rearranging sides is going to be 1/2 and then mv final squared So I'm going to divide both sides by 2 and multiply them by m. So whoops, m over 2. So those cancel, and then I'm gonna do the two things individually. So the two terms individually. I'm not gonna distribute the m. I am gonna distribute it, but I'm not gonna leave it as factored out. So this is what you end up with. You end up with this formula: F net delta x is equal to 1/2 mv final squared times 1/2 mv initial squared. Now this quantity, 1/2 mv squared, and maybe you're familiar with this formula. This is the formula for kinetic energy of a moving object. Okay. And kinetic energy is basically it is the energy of motion. That is the basic way to think about it. Energy of motion. So a moving object, by nature of the fact that it is both moving and has a mass, has some amount of kinetic energy. And the idea is that this kinetic energy can be converted into other forms of energy. Now, usually, kinetic energy of moving objects, when it gets converted, it's usually converted into things like sound or heat. So if you can imagine like throwing a baseball, you throw a baseball really fast, someone catches it with a glove. The baseball had kinetic energy, but when it was caught with the glove, that kinetic energy was basically dissipated into the sound of the catch, so the vibration of the air, and probably some temperature raise in the leather of the glove, and probably the baseball too. So this is how kinetic energy can be converted into other forms. Another example of this, though, you might have is the energy of a moving stream. That would be kinetic energy. What you can do is you can use that energy of a moving stream to turn an electric turbine and basically convert your kinetic energy into electrical energy. Okay, so these are all forms of energy, and one of the cool things about energy is that as the field of science, or as the field of physics sort of evolved, one of the main things to do as that people were investigating new areas was to say, okay, when we're looking at this, what kind of energy are we dealing with here? So what kind of energy do we have when we're dealing with electrical systems, when we're dealing with current, when we're dealing with magnetics? And there is some way, so energy comes into all of these things, okay? So energy is one of these concepts that goes across physics and even into other scientific fields. Like it's relevant in chemistry, biology, all of these things. But kinetic energy is the basic energy of motion for a large moving objects. Some of its attributes: kinetic energy is only positive. And you can kind of see why that's the case. Or zero. Object could have zero kinetic energy as well. But the idea here is that when you square your velocity, even if you're taking direction into account, so you have a negative there, if you have multiple components of the vectors, the formula is a little bit different. Really, it's the speed squared is what that is. But the idea is that you're always going to get a positive number. Mass can never be negative. V squared, anytime you square something, you get a positive number, and 1/2 is positive. So kinetic energy can only be a positive value. Now, what we'll see is that you can have a change in kinetic energy that's negative. You don't always need to gain kinetic energy. Kinetic energy in a system can go down. It can go from a higher value to a lower value, but that's part of a kind of what goes on with this. All right. Now, the other thing is that any moving object has kinetic energy. All right. So two main things to know about kinetic energy is that you can always describe an object in terms of its kinetic energy. And in many ways, the kinetic energy is a more fundamental quantity than, say, its velocity. The kinetic energy is gonna tell you much more about the capacity of what this object can do. Now, kinetic energy is also a scalar quantity. There is no direction to energy. It's just some attribute of motion. There is a vector component to velocity that's relevant, but it turns out that is more effectively expressed in an object's momentum. So really, so no direction associated with energy. Really, kinetic energy is sort of a description of sort of the, so you kind of think about it as the activity of a moving object, if that makes sense. That's basically what's going on there. Now, if we go back up to that equation we just looked at, this one up here, and I'll rewrite this down below. I'll do it in bold. So we have F net delta x is equal to 1/2 mv final squared minus 1/2 mv initial squared. Basically what we have here is we have this thing is actually the object's final kinetic energy, so we'd say K final. And I'll rewrite this. K is just equal to 1/2 mv squared. And then this thing, the second one would be K initial. So what we have here is we have this is a change in kinetic energy. So something about the force causes a change in kinetic energy. Okay, so that's basically what we're saying here. Now, the other part of this thing right here, this is what we call work. Okay, and that is F net delta X is the work. Okay, so we would say W equals delta K. And again, if you have any familiarity with physics, this is the work energy theorem. Okay, now the work energy theorem basically says that when work is done on an object, it changes in it changes its kinetic energy. Now I'm going to make a slight addition. This is the net work done on an object. And this is where some of the confusion comes in, I think, for different for how work is done. But the idea here is that if you have a net force and the object is moving, then basically what you're going to do is you're going to change the object's kinetic energy. Now, it's important to know that F net delta X, basically what this represents something what I like to call work on an object. Okay, so work on an object, basically what I mean by that is that an object experiences a net force and moves in the same line as that net force. Now, what the work energy theorem is effectively saying is this causes a change in kinetic energy. All right. So what I'd like to do is I'd like to go back up to that original question we did, where we have the 30 kilogram box, the applied force of 500 newtons, and the coefficient of kinetic friction at, and it's going 2 meters. Well, so going back to the original example, well, we found the F net. The F net was equal to 470 newtons. Okay. The delta X was equal to 2 meters. So the work on box was then equal to 470 times 2, which would be, what is that going to be? 940. Now, so it's another thing I have not talked about yet. We'll get to this in just a minute. But when you have this work on the box, what you can say is that, okay, that work is going to be equal to the change in kinetic energy. Now, that the kinetic energy, as a reminder, 1/2 mv squared. So your kinetic final minus kinetic initial. And one of the things you can always say that K, not always, but if your velocity is 0, your kinetic energy is 0. That's a fairly reasonable thing to say. So You have K initial would be 0. And so K final would then just be, this would be your final kinetic energy. And from there, you can convert that to 1/2 mv squared. And from there, you can get, all right, V final. So V is going to be equal to 2 times 940 over 30. And then you take the square root of that. And if you do that correctly, you should get exactly the same thing, which I think was 7.92. Yeah, 7.92 meters per second. Okay. Now, we didn't talk about units of energy and work. So we'll talk about that right now. Units of energy and work. And it'll be helpful to remind ourselves of this. So if we look at work, what we can do is we can say, okay, that's F delta X, and the unit is then N. So newtons for force. I'll put the units in brackets like this, and then meters for distance. So this is equal to a Newton meter. Now, when we talk about kinetic energy, this is 1/2 mv squared. The 1/2 doesn't have any units; it's just a constant. But the kilograms would be for the mass, and then the meters squared. This thing would be squared. So the units would be altogether kilograms meter squared per second squared. Well, as a reminder, a Newton was equal to a kilogram meter per second squared. So it turns out that these two, that Newton meters, is actually equivalent to kilogram meter squared per second squared. Those are, in fact, the exact same unit. Okay. Now, it's common enough that both of these, and again, they are the same thing. It's common enough that both of these are just given a new unit, and that is the joule. Okay. The symbol for joule is capital J, and that is the SI unit of work or energy. Now, there are other units of work and energy, really other units of energy. Energy is measured in a lot of different ways and using a lot of different units depending on context. One of a very common way of measuring energy is calories. So calories is more a chemistry thing, and it had to do with how, you know, with when you burn this substance, how much could it raise the temperature of a certain amount of water. It was actually the man the Joule is named for. His name was James Joule. He actually figured out that if you took the kinetic energy of like a falling weight and used it to turn like a paddle system inside a tank of water, you could actually measure the increase in temperature. So it was him that connected this idea of calories, that, you know, when you burn something, you raise its temperature in water, to motion, because it turns out motion could effectively raise the temperature of water as well, you know, if you measured it closely enough. So he was the one who connected these ideas, and you did have calories. Now, the kcal, these are the calories that you read on on your your nutrition labels. I'm gonna look this up. 1 kcal, yeah, is equal to 4,184 joules. Now, they don't call it a kcal, they just call it a calorie. Typically what you will see is you'll see it capitalized, as if that's the case, and those are the calories that are on food labels. There's also a smaller calorie, a little c calorie, which is 1,000 of those is what makes a kcal. That tended to be more useful when making measurements chemistry wise. But nevertheless, that's where the units come from. So another common unit of energy right there. All right. What to do next? Okay. So those are the units. Definitely worth knowing. So I'll do it in orange so you know it's important. Okay. Now I want to talk a little bit about some of the things that can come up. Okay. So I'm gonna tweak the first example slightly. And instead of that, what I'm gonna say is I'm gonna say the box has initial velocity of 10 meters per second to the right. And then the man pushes to the left. Okay. Now, this is kind of an interesting situation. And the reason is that what is happening here is that, and you should think about what, first of all, what do you think will happen just physically? And then what does that imply for the energy? So just writing this down qualitatively can give you a sense, can give you sort of a reality check on what you're looking for in the problem. Now, what I might ask is, how far does it go before he stops it? And the idea is that what you can get is you can hopefully get that um that yeah, if he's pushing against the motion of this box, he will slow it down and hopefully stop it eventually. If it's not too big and things like that. But so the idea is that the man will slow object to a stop. Now, what you can ask yourself is you can ask yourself, okay, what happened to kinetic energy? Well, hopefully, you know that basically it went from a positive value. It had some value if it had an initial velocity of 10 meters per second, and it was removed. Kinetic energy was removed. Okay. So what this means is this means that delta K should be less than 0. Okay. So delta K can be less than 0. And this is what I was talking about before, how you can remove kinetic energy from a system. All right. Now, when you have delta K less than 0, what that is going to mean is that work is going to be less than 0. Because as a reminder, work is equal to delta K. So what does this mean? If work is less than 0, basically what this means is that the delta X is in the opposite direction of the force. Okay. And that is what causes you to have negative work. That is what causes someone to remove energy from a system. Now, that really only works if there's already kinetic energy in the system. You can't have negative work if the system doesn't have kinetic energy. But if it does, you can't exert a force on it to slow it down. Okay. And that's the idea. All right. So in this case, what we would do, our F net is, well, let's take a look at it. Our F net's actually going to be different this time. Okay. Because we know that we have a normal, we have a force of gravity. Those are still going to be equal. They're both 300 newtons. That's fine. And we know that this time the applied force is going in that direction. It's 500 newtons. Again, just tweaking it. Now, we also know that the velocity is in this direction. So velocity equals 10 meters per second to the right. Now, what's interesting here is some people they'll just kind of continue with the free body diagram and they'll say, oh, it's no problem. The friction force is opposite in the direction of is opposite the direction of velocity. The problem is that's not true in this case. Okay. In this case, what you can think about what he's trying to do. He's trying to slow down this object. The friction force is actually helping him do that. Okay. So this is one of those cases where friction is not opposite the applied force. It's in the same direction of the applied force. The friction is not working against him to accomplish this task. It's helping him accomplish this task. Okay, this would be harder without friction. So in this case, the kinetic friction is still just 0.1 times 300 just from the original problem, which is 30 newtons. Now, what this means is that means we have the sum of the forces. And if we want, we can say, okay, we can make these negative. So they're both going left. That's fine. So negative 500 minus 30 would equal negative 300, negative 530, not negative 300, negative 530 newtons. And then the delta X is what we don't know. Okay. So if we wanted to do the work on the box, this would be the sum of our forces in the X direction times delta X. Well, that's going to be negative 530 delta X, and that's what we're finding. So if we're looking for delta X in this case, what we can do now is we can go look at our kinetic energies. Okay, so we can say, okay, we actually know our kinetic energy, our initial kinetic energy, because it's 1/2 mv initial squared. We know m, we know v initial. It's just going to be 1/2 times 30 times 10 squared. That's going to end up being 50 times 30, which would be 1,500 joules. Okay, so that is how many that's how many joules this thing starts with. Now, K final is going to be 1/2 mv final squared. But we are told that this thing comes to a stop. So V final squared is equal, so V final is just equal to 0, which means our final kinetic energy is equal to 0. All right. Now from there, we can find our delta K. And the reason we want that, again, is because work is going to be equal to F delta K. All right. And our delta K is then 15, or it's 0, because that's K final, minus K initial, which was 1,500, which is going to be negative 1,500 joules. Okay, so that is what we are dealing with right now. So what we have here is we have negative 530 delta X, that is the left side, is equal to negative 1,500. And then we just divide and we get delta X, divide by negative 530, divide by negative 530. And it's going to be a little bit less than, 3, but we'll go ahead. And that'd be 2.83. Okay, the negatives canceling out, so 2.83 meters. Now, the idea here is that, again, the delta X is in a different direction as the force. That's what causes, and that is why signs are relevant here. If delta X, because delta X is to the right. So if we've done our sign conventions correctly, then this should work out. The signs should tell us what direction it's going. It's going positive. And since we already defined left as negative up here, then we have a positive force. Then we have a positive force going to the, or positive displacement going to the right, and a negative force. And basically, it was this negative force that was required to remove this object of its energy. Okay, so basically, we could have done this using Newton's laws, then kinematics. We used Newton's laws to find acceleration, and then we find kinematics, and then we do the kinematics to find that. But it turns out that we can do it with this energy method, which kind of skips finding the acceleration. So that is something that can be useful there. So in this case, we've seen that work done on an object can be positive. That was the first example where we added energy to the object, or it can be negative. That is where it removed energy from the object. Now, there's another type of question that can come up, and that is this phrasing: work done by a particular force. Okay. And in this case, what we are doing, if we're asked for something like this, the work energy theorem doesn't really apply. Okay, because the work energy theorem only works if we're dealing with the net force. So remember, this work net equals delta K. This only works. So this is only for F net. If we're looking for the work done by a particular object or by a particular force, then we're not going to be able to use this. Okay, that's what I can't emphasize enough, is that this is only going to work if you're dealing with the net force. So let me give you a an example of something you might be asked here. So the example is in the first question. How much work does the man do? Okay. Now, the reason why you might want to ask this is particularly if it's like a man or an animal that's doing this. Basically, the man's having to spend some of his own energy, or even like an engine or something. It's having to spend some of its own energy to do a couple of things. One, it's having to spend its own energy to give the object this kinetic energy. Some of the energy that the man spends goes into that, but some of it is also used overcoming friction. Okay, so the idea is that you would ask this type of question if you want to know about the inputs from some particular actor into the energy. How much energy did this particular actor have to expend, even if it's unclear that that if I can say this correctly, it's unclear, that he spent this much energy just from the motion of the object. Okay, some of his energy you're not going to see in the motion of the object because basically it was spent to overcome friction. Okay, so in this case, it's not that bad because all we need to do then is the work done by the man. It's basically the force from the man, which we said was F applied, times delta X of the object. Okay. And in the original problem, looking back at that delta X was originally just 2 meters. So we had 500 newtons was his force times 2 meters, and that's just going to give us 1,000 joules. Okay, so the idea here is that this is how much energy the man put into that. Now, what we wouldn't want to do is we wouldn't want to say, okay, the man spent 1,000 joules, so the box has 1,000 joules. That's not correct. That's how much the man spent, but other work was done on the box. And the example for that is, you could say how much work was done by friction. And in this case, the work of friction is just going to be the force of friction this time times delta X. Now, the the um, the the signs here are, if you're being strict, technical, you should make that force of friction be negative 30 newtons, okay? Because the negative 30 is going opposite the delta X. So that would be 2. You do this, you get the negative 30 times 2, and that will give you negative 60 joules. And basically what the negative 60 means is it means friction removed 60 joules of energy. Now, as to what happened to that energy, it didn't just vanish, but it was dissipated into the system. So a couple different ways energy can be dissipated from kinetic energy. And we're not going to look too closely at this. We'll talk a bit about it when we talk about conservation of energy. But a couple of different ways energy can be dissipated. One is through heat. You probably know this, if you've just experienced friction. That the ground and the box probably increased a little bit in temperature. So that's where some of that kinetic energy went. Now, not very much. 60 joules doesn't actually raise temperature very much. But another thing is it went into sound. Now, again, this is something we haven't really talked about, but what sound is, it's the moving of air molecules. So basically, you had the large scale kinetic energy of the box, and some of that energy got transferred into the small scale kinetic energy of the air molecules and, probably the molecules in the ground as well. Sound kind of goes everywhere. So that's basically what friction did. But friction removed energy from the box. Okay. So this idea, and I just want to emphasize this, work by a force can be positive. And basically what this means is that if it's positive, then the force, say positive or negative, just finish writing this, positive or negative. And this is the key word. If you're looking for work done by a force, you're wanting to isolate a single individual force and figure out how much energy that force transferred is the idea, added or subtracted. If you're looking for work done on an object, then you're looking for the combination of all forces. So we'll write that again. But if it's negative, then basically this is a removal of energy. And if it's positive, then this is a gain of energy. Or I'll say an addition of energy. All right. Now, just as a reminder, work on, basically you're going to be dealing with F net delta X. Okay. If you're looking for work by a particular force, this is just going to be F delta X, where F is some individual force. Okay. So that is going to be the main difference for how you will approach these two expressions. And they are different. You will be asked how much work is done on an object and then how much work is done by a force. So I do really encourage you to understand the distinction. But with that, I'm going to go ahead and end this lecture here. Hopefully that makes sense. Please give me emails if you have questions.